Thank you. So I've been working on spectrum monitoring for the last 2 years or so, and I'm going to give you some of the insights that I've been gaining over the time. And let's see, yeah, this goes to the next slide. So the traditional way of doing this is actually using, let's see if that mouse here works. Yeah. Okay, so the traditional way is using a big truck with about 500,000 worth of equipment, and then you drive that truck to some location, you make measurements for a month or so, or maybe a week or so, and then you bring those back eventually into the lab. And the alternative to that is to have several smaller things that cost much less, and you put those in various locations, and you can actually then simultaneously look at the spectrum in many different places. So that would be a network of configurable sensors. And the real question is, you might have a budget that can buy one of those things here on the left. Okay, those are about 100K plus. Or you can maybe buy 20 of single board computers and SDRs and make your own spectrum analyzer out of it. And so the question is now, what exactly are the trade-offs that you run into, and what do you need to do for making this successful? So we're going to look at radio receiver architectures, spectrum signal analyzers, spectrum/signal analyzers, performance measurements and results, and future directions. And as we go along, I will sprinkle in some measurement terms, procedures. There is more in the paper that actually goes with that. It's a separate appendix there. Okay, so first of all, we look at radio receiver architectures. We look at frequency translation as being one of the basic building blocks when you build radios. And then the two main architectures, the super heterodyne receiver, SHR, and direct conversion receiver, DCR. I did not put in the direct RF receiver technique that has been talked about by Analog Devices just a little bit ago. Okay, so here is the frequency translation. What you do is you basically have a multiplier, and you multiply two sinusoids together in the simplest case. And when you multiply two sinusoids together, then you get out the sum frequency and the difference frequency at the output. And one of the two you're going to filter out with that filter. So graphically, that's what this looks like. Up here is a signal that sort of represents graphically what could be a radio signal. And I used for the positive and the negative frequencies different colors so that you can see how this combines together. And then you multiply this with a mixer, which is just a sinusoid. And that mixer in the frequency domain is just two impulses. And you convolve those things together so the actual radio signal just gets placed to where the impulse is on the right side and on the left side. And so you're getting this radio signal shifted over to the right here to the positive frequencies. And from this one, you get it shifted over to the left frequencies. And then it gets combined together. Of course, it gets added together. And so you get a new radio signal with actually reversed positive and negative frequencies, but that doesn't matter for a real-time signal, for a real valued signal. And you get the other one that's way out here. So you get one which is at the higher frequency and at the lower frequency, and you choose which one to keep. For example, with a low-pass filter, you keep the one here in the, close to 0. With a high-pass filter, you keep those which are out at the higher frequency, the sum of the two carrier frequencies. And then you apply that principle to do something like the super heterodyne receiver that has been around for quite a while. And the actual stage where you move things, where you shift things in the frequency domain is this stage here. And then at the output, the bandpass filter, that's the filter that picks what frequency you want to continue with, and that's typically the difference frequency. And then you build a bandpass filter for that and an amplifier, so that's what the intermediate frequency amplifier is in a conventional radio receiver design. And there are some things that you have to pay attention to. There is an image frequency, and so you need a bandpass filter in front of that, and then there is typically a low noise amplifier at the RF domain, and in front of that you need another bandpass filter, so you add up essentially the whole thing to 3 bandpass filters if you want to do this right. And that's just a single conversion super heterodyne receiver. Typical high precision instruments would use 2 or 3 stages of that. So let's look at that. Actually first at the history, and then we will look at some details of it. So it was invented around 1918. There is a dispute on patents of who did it first, but Armstrong is generally considered to be the one who really understood what he was doing, whereas the other one was actually using the super heterodyne for a different purpose. So what Armstrong actually wanted to do, and that's written in his paper here, a new system of shortwave amplification. He really wanted to actually amplify the signals by a lot, and he realized that this could not be done easily at RF frequencies, that he needed to do that at lower frequencies. And the reason why he wanted to amplify them is because in any AM receiver, you need diodes in some places. So in this case, there is a diode actually here. That's a vacuum tube in his days, and another diode here. And the diode acts as a squaring device. So if you take some small number and you square it, that becomes an even smaller number. And so that means that you lose intensity in your radio signal. And what Armstrong wanted to do is to amplify this so that he can get a more efficient rectification of the signal or passing it through the diode. Okay, here is an example of how this was implemented in his day. Okay, so now the image frequency that I mentioned briefly. Here we can look at it graphically. Basically what you get here after the mixer is the difference of 2 frequencies. So there is frequency C, which is a carrier frequency, and frequency X. And one of the 2 is going to be bigger than the other one. But you can have it both ways, and so that's what leads to 2 frequencies from the input that can actually pass through this IF amplifier. Graphically, it looks like this. If you assume here the cyan portion is one radio signal with marked with triangles here, and the purple portion with rectangular spectrum is a second radio signal. If they happen to be to the left and to the right of the actual mixer frequency fx here, then when you mix them down by multiplying by fx, that fx goes down to 0 from the right, and it goes up to 0 from the left. And so that produces this whole spectrum here shifted to the left, this whole spectrum shifted to the right, so it adds up at the low frequencies, and you also get a term at 2 times the frequency, or at the sum actually of the frequencies, which is out here and out here. So only the middle portion is passed by the intermediate frequency amplifier, but both the cyan portion here and the purple portion, they actually get added together and go out through the IF amplifier. And you only want to have one of those 2 signals, so you need to have a bandpass filter in front of the mixer in order to reject one of the 2. Okay, and so that has been a problem in general for super heterodyne receivers, that you need to suppress that, and that actually requires that you have both of those filters here in general, one to protect the input amplifier here, and the other one to actually reject the image. And you cannot, for example, leave out the second one here, because otherwise you get all the noise from the preamplifier from the image channel, even though you don't get a radio signal from that. So that would reduce the noise figure, or actually increase the noise figure of your receiver. Okay, so the advantages of the super heterodyne, you have no local oscillator leakage. We will see that when we talk about the direct conversion receiver. Then the RF band select filter suppresses out of band signals before the low noise amplifier, and that's actually significant. It's not affected by second order nonlinearities, which I'm not going to explain right now. And then disadvantages, you need to reject that image frequency. You need 3 bandpass filters if you do it right. Some must be tunable if you want to tune over a wide range. And it's difficult to integrate the bandpass filters with high Q, high quality, on a chip. So basically, you cannot do a system on a chip in implementation in an easy way, like, for example, the analog devices chip that's in many of the software-defined radios. Okay, the direct conversion receiver, also called Homodyne or Synchrodyne receiver. Here is a block diagram of the modern version. So you have also the front end with a bandpass filter low noise amplifier, but then you mix down directly to baseband using a cosine and a sine as the local oscillators, and that gives you the I and Q outputs of the IQ signal that you get in the end, the in-phase and quadrature signals. So you mix down directly to baseband. You have IF equal to 0, so that means you're not going to have an image frequency. You filter at baseband, typically using digital signal processing, so you don't need any bulky filters or so at baseband. And you do minimal signal processing at RF frequencies. Here's the origins of that. This one over here is 1924. And the idea was actually similar to what Armstrong did. They wanted to increase the amount of energy or voltage that they have from a received signal so that they can do rectification using diodes. Here is from a patent of 1936 that shows basically the IQ version that we are used to now, but it has been used for something different. It has been used to actually suppress overlapping sidebands in radio signals that are too close together. Okay, the modern form of the DCR with explicit IQ signals at the output seems to have appeared only about late 1970s or early 1980s. And part of that is that highly selective low-pass filters are actually expensive to make when you have to make them in the analog domain with L's and C's. They are easier with op-amps, and they are, of course, very easy when you have digital signal processing available. Okay, here's the complex valid form of the direct conversion receiver. Instead of using sine and cosine separately, you just simply multiply by the complex exponential, e to the minus j 2 pi fx, and using the Fourier transform relation for frequency shift, that brings it down to baseband. And here's a graphical representation. You have here a radio signal, a schematic radio signal. You shift it to the left by fx, and then you use a low-pass filter, so you keep only the purple portion or whatever was at the positive frequencies in the frequency domain before. The advantages is, again, you don't have any image frequency problem because the image frequency, because the intermediate frequency is equal to 0. Most filtering is done at the baseband, so you can use digital signal processing, and only one local oscillator is needed, so that results in less phase noise, for example. Disadvantages is DC offset and spurs that you get from LO leakage. So if you go back once more here, because this whole chain here all operates at the radio frequency that you want to receive, and this one here is tuned to the radio frequency that you want to receive. There can be feedback from here back into the low noise amplifier and go through here, and that leads to oscillations that then creates spurs, as they are called, in the output spectrum. And also you can get DC components, IQ imbalance between the sine and the cosine oscillators, which leads to crosstalk between the I and Q channels. And another problem is flicker or 1/f noise that you do not have at higher intermediate frequencies, but once you go down to baseband, then you're operating with low frequencies, and you're going to get some of that noise. And that affects everything. CMOS transistors, or in the old days vacuum tubes, they all are affected by 1/f noise. Okay, there are other effects for both the super heterodyne and the direct conversion receiver. All amplifiers that you have at some point exhibit some nonlinearities, and mixers, of course, are inherently nonlinear devices. So you're going to get nonlinearities through the whole chain. Third-order intermodulation products affect both the software, the super heterodyne receiver and the direct conversion receiver. Second-order products, which are called Im2, they affect mostly the direct conversion receiver. Phase noise of local oscillator affects the super heterodyne more than the direct conversion receiver. Modern implementations use sampling and analog to digital conversion once you are at baseband or at intermediate frequency, and then the dynamic range is directly affected by the number of bits of your analog to digital converter. So the best that you can hope for with 8 bits is about 50 dB. It's usually less than that because there are other effects besides the quantization noise from the A to D converter. Okay, so now this looks intimidating. That's an attempt to talk about the intermodulation products. And the main takeaway here is that when you go into the nonlinear region, the way you model this is in the form of a Taylor series of your signal. So x of t here, that's your signal that you want to model. And then you also get some x squared of t and some x to the 3 of t because of the nonlinearity. You also get a DC component here, which is less important. And each of those appear with certain factors. And so what you do in order to test for that is you make a signal that has 2 tones to it, like a frequency 1 and frequency 2, usually relatively close together. And then when you take now the square of the signal, then you're going to get the first thing squared plus the second thing squared, and then the product of the 2 of them. And the product of the 2 of them, that's this term that is shown here, cosine of 2 pi f1 minus f2t. Because f1 and f2 are close to each other, that means that you're going to get the component at the low frequency. That's why it affects the direct conversion receiver. And then you do the same thing by taking the x to the 3 of t. So you take this sum of the 2 cosines, raise it to the 3rd power, and then at some point you're going to get a term in there that contains 2 times the first frequency minus the second frequency, or 2 times the second frequency minus the first frequency. And because f1 and f2 are similar to each other, that will result in a frequency that's similar to either f1 or f2. And then to measure this whole thing, you may have seen that in specifications, the Ip2 and Ip23 measurements, you basically try to figure out what those coefficients K2 and K3 are. And the way you do that is you look at those additional frequency components that are being generated, and you relate them to what your actual frequency is of the transmitted signal. Okay, so more details are in the paper that goes along with that. In general, larger values for Ip2 and Ip3 are better. Okay, now looking at spectrum or signal analyzers. Here is a selection of a few old ones. During World War II, they used spectrographs, as they were called, which used a piece of paper that's rotating around and recording whatever the spectrum is for analyzing voice signals that in those days were encrypted by just shifting the frequency range of the signal. This was the first calibrated 2 mega spectrum analyzer in 1964 with a 2 megahertz sweep width. This one is the control panel of the first spectrum analyzer that used the FFT for the computation of the spectrum, and the 1024 point FFT took 1 second. That was 1967. Okay, so spectrum analyzers display signal power versus frequency. There are 2 broad analyzer categories, SWAP-tuned ones and FFT-based ones. The SWAP-tuned ones, they show magnitude only, and that is shown sequentially for different frequency bands, so you don't get to see all frequency bands simultaneously. The FFT-based ones, they record basically a time sequence, and then they use the FFT to compute what's happening in the frequency domain, so you get to see both magnitude and phase, and you have all frequencies simultaneously. Most professional spectrum analyzers use a super heterodyne receiver front end, and then the ultimate, in a way, of spectrum analyzers are vector signal analyzers, which allow you to look both at the power, but also analyze modulation signals and other things directly from the IQ samples. Okay, here is a block diagram of a modern spectrum analyzer. That's the one that is 100K plus. So the thing that you can see here, there's a filter here, there's another filter here, there is a local oscillator here, there's another local oscillator and mixer. There are 3 stages of mixing here, so this is a triple conversion super heterodyne receiver. There is another filter bank here with 4 filters, there's one with 3 filters. So all those filters, they are very big, expensive, time-consuming to adjust and everything. That's why this thing costs 100K. Okay, so now to reduce the cost, software-defined radios use typically the direct conversion receiver architecture with a minimum of RF filtering. In fact, this first bandpass filter is usually omitted on the software-defined radios. They can be implemented as a system on a chip, and we have seen the analog devices chip here in previous presentations. The SDRs are calibrated for frequency, but not for power. For frequency, it's relatively easy. For power, that would be much more time-consuming. The higher-end SDRs have FPGAs for onboard digital signal processing. Most signal processing and all display functions take place in an external computer, like, for example, through GNU Radio. SDRs can act as vector signal analyzers because they give you the time sequence output. But the ADC resolution and bandwidth are typically more limited of those than they are of those 100K spectrum analyzers. Okay, so now here's a typical block diagram of one of those. So you can see here, this is the basic block diagram. There is the receive antenna, and then it goes into the AD9364 integrated circuit, which has a block diagram down here. And then you basically do the digital down conversion. Here's the receive pass. And you go through the FPGA and out through the USB 3 connector. So what you notice here is that there is nothing like that RF band select filter in front of the low noise amplifier. The low noise amplifier, that's inside the AD9364 chip. Okay, so now that's just something to keep in mind as we now take a look at measurement of those things and performance of those things when you use SDRs. So first of all, you have to calibrate your SDR if you want to get any meaningful results for spectrum measurements. And that means that you have to basically go from frequency to frequency, roughly in about 100 megahertz steps. We do that from 100 megahertz to 6 gigahertz, and you have to note how much power do you give at the input, how much power does come out of it, and then you have to make a calibration table based on that. Then you want to measure the noise floor and the noise figure versus frequency. You want to measure the 1 dB compression point versus frequency. So that's the point where you start going into the nonlinear region. And then there's a number of other things that you also might want to know about, but those first 3 are probably the most important ones that you need to get the basic function as a spectrum analyzer. Okay, so now talking a little bit about gain factor calibration, and that's actually my only diagram here that I have which does use GNU Radio. So you get your radio frequency signal in this case through a Pluto SDR, and then I split it up here into real and imaginary part, and then you have to multiply this by a constant that is to be determined, and then you get an in-phase and a quadrature component out, and you have to ask yourself now, and how do I calibrate this thing? You have one input here, but you have 2 outputs because you're now operating in the complex low-pass domain. So what do you do? Should that output here have the same amplitude as this input, but because you have 2 of those, you're going to get too much, possibly. Or should you make it such that you kind of evenly split up between this one into those 2 back here? And after all, there is going to be a frequency involved for the transmission. So that's the CW signal here, the continuous wave signal that runs at FC. And then you have some frequency FX that's determined by your software-defined radio. So you're actually not going to receive something at an exact frequency. There will be no exact frequency or phase relationship between the transmitted signal and your SDR that's actually receiving it. So your only really good way of calibrating this is by actually looking at the power of this here, which is the in-phase component squared plus the quadrature component squared, and make that as a relation to this actual received power. And then you adjust your constant K in here so that you know what that relationship is between the power here and the power in the digital baseband output. Okay, this basically shows the computation for that, but I'm going to skip it for timing reasons. But essentially what you do is you take your received signal, A times cosine 2 pi FCT, which is a CW signal, and you actually use a factor of 2 as one possibility of how you can calibrate this. There is no single right way for calibrating. So we chose to use a factor of 2 here so that the signal in baseband in the in-phase component is actually looking the same like the component that you actually received. And that means then that you're going to get actually twice the power in the complex baseband compared to what you had at the RF frequency, and you have to just simply take that into account. Okay, so here's what some of those measurements look like. This is a mid-grade SDR, something that costs about $1,000 or so. So you see those curves here, those are the gain factor calibrations or the gain factor measurements for different frequencies that goes here from basically 100 megahertz to 6 gigahertz. And the different colors is for the different settings that you put on the SDR of how much that SDR is amplifying. Then you look at the dynamic range that the whole thing covers. So you have the curve here at the very bottom is the noise power that you get when you use a Fourier transform and you use just the power in a particular bin in the Fourier transform. The red one is if you just look at the noise floor across the whole bandwidth of the receiver. And then the blue one at the top here, that's the spur-free result. So meaning that you have not gone into any kind of overdrive yet, so that you don't get to see any additional frequency components beside that continuous wave component that you put in. And the red here at the top, that is the one where you run into the 1 dB compression point. So it's safe to say that the dynamic range is essentially between the 2 red curves in here, and it gives you approximately 60 dB in this case. This is an SDR that uses 12-bit analog to digital conversion, and that's consistent with that 60 dB. Okay, here is an economy grade SDR. That one only goes from 100 megahertz to about 1.7 gigahertz, so it's basically one of those RTL SDRs. You see the gain factors here again for 3 actual gain settings on the SDR that we have been measuring. When it goes up here towards the higher frequencies, that means that the gain goes down of the actual device, so that you have to increase the gain factor calibration. And here's the dynamic range for that, so that gives us something on the order of about, oh, this doesn't show the upper and the lower limit, that shows just the dynamic range itself. So you can see here it's a little bit less than 50 dB, which is consistent with an 8-bit A to D converter. Okay, then once you have now your sensors, then you put those into a network, and that is called the spectrum characterization occupancy system, and that's actually is in the process of becoming an IEEE standard. At NTIA/ITS, we made a first reference implementation of that, and we used that in the Boulder wireless testbed in Colorado. One of the features is that this is hardware agnostic, so you can integrate many different kinds of sensors into it. It has a web-based interface for sensor tasking, and the data is collected using SIGMF metadata format. And we have several sensors of that installed in Boulder, in particular several ones on the CU campus. And so here are some of the results that we're getting from that. This is from an LTE signal, an uplink signal, and you can see up here what the spectrum looks like. So these are individual transmissions. You see down here in the waterfall plot some of the resources that are being used for actually the mobiles that are transmitting through the uplink channel. Okay, then we put this out on several ones, and I made simultaneous measurements actually during a CU football game to see what would that look like. And there are interesting things to see here. So this is actually one that looks good. That's from a station that was far enough from the actual football field. This one here actually looks kind of strange. You can see that the noise floor, which is somewhere out here, is way too high. It's about -110 dB, whereas here in this case it's -120 or even less than that. And so once we looked at this in the time domain, then we see this picture here. So what you see on the left here, that's basically just overdriven. Okay, the sensor actually happens to be in close proximity with either the AT&T or Verizon downlink, and so it's just overdriving the whole thing, whereas the sensor that was far enough away has a time domain signal that looks like this. Okay, and so what does that mean? It means that the input of the sensor is actually, in this particular case, it's blocked or desensitized by that strong signal that is out of band. Okay, and here is another example. This is a frequency that's different from the one where that saturation occurs. It's an uplink signal, so you can see uplink signals here, but here you don't see any of that. And here you see that the noise floor is at -160 dB for the sensor that was far enough away, and the noise floor for this one is something like -140 dB or so. And so basically that means on the left side here, that spectrum is useless. That plot is useless because whatever signals might have been there is actually wiped out because of that signal that you have in a different band that is strong enough and overdrives the input amplifier, the RF input amplifier. So the lesson to be learned is that when calibrated, the selected mid-grade SDR actually performs very well. Gain, noise figure, and 1 dB compression point calibration versus frequency is necessary for each unit. It's time consuming, but it can be automated. The major problem is actually overdriving of the RF front end by strong out-of-band signals. And in a regular spectrum analyzer, you have plenty of filters and stuff in there that you can switch in order to avoid that. And you usually also have a larger dynamic range. With a software-defined radio, you don't have enough dynamic range, and you don't have any protection of the input for out-of-band signals. So you actually have to put that there yourself, and you just have to be aware of that. Once you do that, then it actually works quite well. Okay, some future directions. We want to increase the number of sensors, decrease cost and size, and eventually we would like to actually make a mobile network by putting some of those sensors, for example, in public transportation vehicles. Then we want to use the sensor network for real-time RF propagation measurements, exploiting existing transmitters. You know, there's all kind of LTE transmitters around, for example. You can use those as transmitters, and then if you have a network of sensors, you can look at what the signals look like in different locations, and you can infer measurements of the propagation in this way by synchronizing the reception of your signals. Then we want to use machine learning to deal with sensor imperfections. Besides that overdriving of the input amplifier, another problem that you get, of course, is spurs at some of the frequency and the DC component, and 1/f flicker noise. So a machine learning algorithm can learn what the impairments are of your software-defined radio and hopefully deal with that. And another use of machine learning that we want to pursue is to identify network anomalies and locate unintentional and intentional RF intruders. And last but not least, I would like to thank my colleagues at ITS for actually working on that. Originally, it was planned that we have a joint presentation of this, but because of some reservations that the government has that you cannot endorse things and so forth, it would have had to go through a review process that would have taken too long, and so I couldn't include those people. But as my role of university professor, I'm actually relatively free to say what I mean to say. So I guess that's it. There's a lot of formulas probably in there, but we did actually learn a lot of things, and even though I thought of myself as being relatively knowledgeable in RF things and SDRs and so on, I actually had to really sit down for about a week and really think about all those things. And I included that all in the paper that goes together with that, so hopefully that will be of use to somebody.
Thank you very much, Peter.